somebody should be responsible to tell me always to start the recording. This is it. Okay. Anyway, you have this discussion on the other recorded laboratory. So, classification of the instruments. We have 3 criteria. First of all, the pressure value, which you see goes around, turns around the atmospheric pressure. So we are speaking about manometer and micromanometer, measuring relative pressure greater than the atmospheric one. We have vacuum meter or microvacuum measuring pressure below this atmospheric pressure. Now, my question is, to what refers this term micromanometer? To the dimension of the instrument or to the value that is measured, the pressure value? What do you think?
The pressure value.
Of course, the pressure value. So micromanometer will measure what? Or vacuumeter? Will measure very
10 to minus 6 bars usually.
Yes, if it's very special one, but generally very low pressure. 10 to minus 6 what? 10 to minus 6 bar.
Bar, yes.
Yes, 10 to minus 6 bar, you are right. Okay, so very low values of the pressure. Then there are some instruments that can operate as monovacuum meter. I mentioned when we discussed the graph that where I mentioned that atmospheric pressure is taken as zero reference. So generally there are the instruments with elastic elements, a substance that can operate like this, but unfortunately the variation domain, the measurement domains is reduced until is limited to 25 bar. And finally, the barometers, where they measure what we denote by B or P atmospheric. It is not a mistake here. P is the notation for absolute pressure, but we are allowed to put the sign equal because, for example, a compressor for the intake air, it takes the air from the surroundings, which this air is at atmospheric pressure, and of course this is the absolute pressure at the intake. Otherwise we would say that it's a relative pressure and we would consider twice this atmospheric one, which is not correct. All right, the purpose of the measurement, I mean the purpose and the accuracy as well, because they are connected. We are speaking about standard gauge, which are used for calibration, so are expensive instruments, and they are kept at Metrological Institute, and of course have a very high accuracy, so-called metrological one. If we have lost the scale, in that case we can ask for a standard gauge. With a lower accuracy compared to the metrological one, we have what we call model gauge, which are used to verify the regular instruments if we have doubts about their operation. And finally, the industrial gauge, which are currently used in the measurements. And finally, the last one, which is the most important for us because it will be followed in the presentation, upon the operation principle, we can have those operating on hydrostatic principle, measuring the deformation of the liquid column. So you see now the substance, this substance mentioned here, yes, this substance will be different. So we have for the hydrostatic operation principle, the liquid. For aneroid or elastic element, we have the deformation of this mechanical elastic element. And let's say mechanical elastic element, and for the last one, we can use some electrical application, namely the passage from pressure to variation of an electrical property. This time there is not very much the same idea. I mean, comparison with the atmospheric pressure, because it belongs to another category. But we mention here as well. The description of the instruments, we start with the hydrostatic gauges, mentioning that what is interesting, or what's the answer of the instrument, is the height of the column that is created due to the force of gravity and in correlation, of course, with the pressure that is to be measured. Instruments here belonging to this category are the liquid column gauges, using either water, either mercury, alcohol, or oil derivatives. And from this we will pay attention firstly to U-tube manometer, because this U-tube manometer is widely spread and it has a lot of application, we will see. First of all, let us mention that it can be used as manometer, vacuumeter, and what we will present at the end of these hydrostatic instruments, differential manometer. Let us have a look to this representation. So it consists of a U-tube, generally in glass, filled with liquid, which in equilibrium states everything should be the level in the two branches at 0. Generally, one branch is connected to the pressure that is unknown, and the other one is free, letting the atmospheric pressure to act on the liquid. How we determine the pressure using the indication of the apparatus is given in this short derivation, but first of all, let us have a look what's happening here. So when we apply this relative pressure, it will determine the liquid to rise in the left branch and to create actually a height difference of H total. H total that is advised, as it mentioned here, yes, to be read separately on two branches, from the 0 reference of the scale to the top on the left branch and to the 0 to the bottom on the right branch. Well, I didn't mention at the beginning, but I mentioned several times during my presentation that not everything is written on the presentation. You are supposed to complete with what I am saying extra. For example, the comments of this one is not mentioned, only put it here an attention sign. But the question of for the lab exam could be of this. For example, why are you supposed to read separately the height of height H1 and H2? What consequences should should have the reading of only one height, and that is then multiplied by 2. So, of course, there are logical explanations. Some of them you can know. I will give you some ideas. So, first of all, if you did not pay attention at the beginning, if the level of the fluid in equilibrium is precisely at 0, if it starts, for example, for a lower level, you risk to have wrong information if you read only one height, for example, H1. Yes, because it will be smaller than as it would have been from 0, and then by multiplying by 2, you will get a smaller answer. Moreover, this is a glass tube, yes? During the fabrication, there could be on this branch a small diameter variation, and this diameter variation could cause an error, of course, in reading H1. If you multiply H1 by 2, you will multiply this error. You are supposed to know that who reached us? Mihai, what have you done until now, Florin? Florin. Wow, you are on the street? What are you doing? Florin, do you hear us? Do you hear me? He's here, but he's not here. Okay, doesn't matter. So, what was I saying? Okay, we have spoken about errors, but we also have to mention that this is a quite enough accurate instrument. You are supposed to read a quarter of millimeter. So a quarter of millimeter water column is 2 Pascal, yes, around 2 and something, almost 2.5, so quite enough for readings. All right, how we determine the relative pressure, starting from the definition, you see, the weight divided to the cross-sectional area. The weight is mass times gravitational acceleration, because this pressure is created by the gravitation. If you replace the mass by density times volume, and the volume by area, cross-sectional area times the height, you will get this very well-known expression, where h, again I'm insisting, is the sum of the two heights read from zero level to the top and to the bottom. The main disadvantage is that the operation range stops around 3 bar to maximum 3 bar, because the branches needs very long lengths, and the instruments become fragile and difficult to handle. Now, let me ask you, and this remains for you to complete, and could be a question for the lab exam. You have to measure small pressure. You know that it's question about a small pressure. And you are allowed to choose the liquid inside such a thermometer. What would you choose between water and mercury? What's the aim, actually, of the choice? To emphasize?
Water, probably.
The water, says Miruna. Why water, Miruna?
We want a liquid that will show the greatest change in length.
Yes, we need a liquid with great change in height. Otherwise, and this is caused by what? If we look to the expression, G is fixed.
By rule.
So we can make a trade-off between density and height. If we need high height, so a small pressure, we will use, as you said, a liquid with small density. Comparing the density of water with that of mercury, there is a quite huge difference. The water has 1,000 kilogram per cubic meter, while the mercury has 30,595. So 30 times, almost 40 times greater. All right, excellent. So you will be able here to derive the equivalent in millimeter water column of another liquid height. So what you have to do is to express the same relative pressure, because either with water, either with mercury, we measure the same relative pressure, and to determine the relation between the two heights and the two densities. It remains here for you to complete. Then we mentioned that above 3 bar, the instrument becomes fragile. So this determines to be replaced by this single limb liquid vertical column manometer. Very long title, but this is it. What's the main advantage? The fact that we do not have this disproportion of the two section creates the main advantage, and also the fact that in this case, having a reservoir, we can measure also higher pressure. What changes here is the fact that we have different cross-sectional area, not the same. So they will change a little bit the answer, or the way that we compute the pressure based on the answer of the apparatus. Namely, we still have the total height in discussion, just that we don't have control of this height where the liquid goes down in the reservoir in order to get to rise in the tube when the pressure is, relative pressure is applied. But by equivalence of volume, we may have this H1 in the reservoir being a function of the two cross-sectional area, and H, the information that we can read. And in this case, we have this expression. Now, the idea is that for such apparatus, what is called the constant of the apparatus is everything except H. So in this case, it's density, gravitational acceleration, and the parenthesis that groups the constructive values of the cross-sectional area. What I did not ask you, in what operation mode is used this U-tube manometer in the picture? As manometer or as a vacuumeter?
Manometer.
Manometer, why?
Because it's close to the atmospheric pressure.
I wouldn't say it's close to the atmospheric pressure. You may have here H total of 2 meters. Yes, it depends on the height of the column. But your answer is correct, and you have to find means to explain it. Comparing, of course, the two pressure, because this gives the answer. No, this is the operating principle.
You wouldn't be able to find if it would be a vacuum meter, the pressure would be too small. You wouldn't be able to calculate it because the difference in heights would be very small.
No, not this is the idea, Andra. Of course, that the height is depending on the value of the pressure, but the idea is that here you compare, or the apparatus, actually, instruments compare the pressure to be measured to the atmospheric one. If here, because the column rises against the atmospheric pressure, it was at 0 at the beginning, yes? And now the liquid is pushed against the atmospheric pressure. It means that this relative pressure is greater than the atmospheric pressure and determines this displacement of the liquid. Okay?
Okay.
How high is this H total? It depends, of course, on how high is P relative compared to the atmospheric one. If it would work as a vacuumeter and you want to keep the same representation, what would you do? So now the vacuum pressure is lower than the atmospheric one.
The change in height would be on the other side of the
Yes, this is change the two pressures, yes? The relative pressure here and the atmospheric pressure here. And then it is the same deformation of the column because the atmospheric pressure is higher than the vacuumetric one. Excellent. Now, going back to the other apparatus, what's happening here? Here, compared to the previous one, we have a constraint. The idea is that we can read only this height, yes? This is, so we always have to push the liquid in the vertical tube. Now, in what is represented here, the instrument operates as manometer or vacuumeter. Again, the same comparison gives you the answer. But maybe other students could also contribute, not only Andra. Well, now position Diana, you didn't say anything. I didn't hear your voice today. Are you with us? Diana. She's not with us. Andrea, you will still with us?
Yes.
Okay.
It's the same.
It's the same what? Manometer or vacuumeter? This was the question.
The one of the left.
Yes, the left is the pressure to be measured, the relative pressure. And here
it has to be bigger.
Yes, in order to.
Than the atmosphere pressure.
Yes, you are right. And in this case, what's the name of this pressure?
Manometer.
Yes, excellent answer. So it's operating as manometer. Andrea. All right. And if we want to use it as vacuumeter, what we have to do? Juana, we didn't hear your voice today. Juana?
Yes.
Can you give us an answer? The question was, we want to use this apparatus as a vacuum to measure a vacuum pressure. What we have to do? We need to have the liquid in the vertical tube. Otherwise, we cannot read the indication of the apparatus. So,
I don't know, switch the pressures.
Yes, we switch the pressures because in that case the atmospheric pressure becomes greater and here will be a lower pressure, so we will get precisely the same representation. But we didn't mention that here, if we let like this the two pressures, I mean, and the relative pressure will be a vacuum pressure, doesn't matter. The column will uh, rise up in the right branch, and we can read as well H1 and H2. Contrarily, here we cannot do this because we always have to force the liquid to rise in the vertical tube. So we have to change the two pressures. Otherwise, it's useless to have this apparatus. All right, I think that we discussed enough about it. Let us pass to the last, not the last one, the third one, which is the same liquid incline column manometer. Why do we use this? Because it's the only one which can measure low pressures, order of magnitude millimeter water column. And you have seen the power, if I can say like this, of this 1 millimeter mercury water column. Consequently, this low pressures indicates it as operating as micromanometer and micro vacuum meter. So again, low pressure that is measured. Now, what the particularity of these instruments? The fact that we are not, that there is not anymore available the height of the deformation, but the length of the liquid that is dislocated in the inclined tube. But the expression remains the same, the sum of H1 and H. It means that we will have to find a way to express the height that corresponds to the liquid dislocated from the reservoir and a way to express this height corresponding to the length of the liquid that entered in the vertical tube compared to the zero level in equilibrium. Of course, the first one, H1, is already known. It's a question of volume equality in the reservoir and in the tube. And the second one, once the apparatus is built, the angle is known. So applying a trigonometric function of sinus, we have also this information that we are looking for to connect as a function of L. Now, when we put together in the previous expression, we will get a similar expression as previous, rho, J, H that is red here, which will be replaced here by L. L will be red, yes, and the parenthesis will contain constructive elements, the angle and the ratio of the two surfaces. Again, the constant of the apparatus contain all properties except the answer, which is given by L, the length on the inclined tube. It is not necessary to say, we mentioned in the beginning, so the order of magnitude is around from 0 to 50, 60 millimeter water column. And to finish the discussion, the two last instruments are the differential manometer. It's actually a U-tube manometer, which receives information at both branches. So both have relative pressure as information. There is no atmospheric pressure that enters in discussion, which means that this differential manometers gives directly the pressure difference between the two Actually, not the values of the two pressure, but the pressure difference corresponding to the deformation of the column on the height h. My question is, when you use in a experiment such a differential manometer, you have got this h, you transfer it by the density and gravitational acceleration in a value of pressure in Pascal. How will you consider this pressure in your calculation? As relative pressure or as absolute pressure, being a difference of two pressures? Either Mircea, either Dragos, either Ioan could answer. So we expect an answer from you for this differential manometer. How do you use the information that it provides? I mean difference between two pressure in further calculation. Do you consider it relative pressure or absolute pressure? I mean, the difference is the fact that you have to add the atmospheric pressure, yes?
Yeah.
You will add it or not? This is the question.
If we add it, I think, yeah, we do have to add it.
Do we have to add it?
Yeah.
And how? We will do the sum with the apparatus information or the difference.
We do the sum with apparatus. We do the difference.
We do the difference.
With apparatus information. Yeah.
So we will write B minus rho GH. This is your proposal?
Yeah.
Okay, everyone agreed with him? Well, Dragos? Dragos, you are with us?
Yes, I'm here.
Okay, so you agree with Mircea?
Yes, we do have to consider it.
Okay. Ioan?
Yes, I'm here, but I don't know.
Ioan, can you answer us?
Yes.
We do not hear you. At least I do not hear you.
We can't either.
Okay. So,
Wait.
Andra?
Hello?
I don't think so, because there's no, it's only P1 and P2 from two separate gauges.
So, it's relative pressure or absolute pressure? Considered. Relative. Mirona?
Yes, it's relative pressure.
Okay, so the conclusion is that all of you will do a huge mistake in further calculations. First of all, in order to use the atmospheric pressure in an absolute pressure calculation, you have to know the relative pressure. What is it? Manometric or vacuumetric? Otherwise, you cannot use that formula. Here, you have no information. It's just a pressure difference. Yes? But if you think that P1 could be whatever, either manometric, either vacuumetric, and you will express it as absolute pressure with B involved, and P2 the same, when you do the difference, B, the atmospheric pressure, will disappear, and you will remain only with this information, rho GH, as absolute pressure. Okay, so be careful. We mentioned that the instruments generally gives relative pressure, but not here when it's question about difference, because the difference will make disappear the atmospheric pressure. and it is not worth to add it. You do not know what to do with, to put it a plus in between two terms or a minus, okay? So be aware that the differential manometers, its information is directly absolute pressure. And to finish the discussion, yes, Ioan, you want to
Now
say
you can hear
something?
me?
I'm hearing you, but very low.
I don't know what's the problem. I have the microphone in front.
Now
but
it's okay. Now it's okay. Maybe
now it's
you.
like that.
Yes, okay. The next question will be yours. Don't worry. The barometer not belong to this type, the modern barometer, I mean, belongs to aneroid instruments, but the idea, the initial, the origin of this barometer actually belongs to this class. I don't think it's something new for you. The principle was to turn tube filled with mercury in a bath of mercury, which has here an orifice allowing the atmospheric pressure to act on it. At the level of the mercury from the level of the mercury in the bath and the height where the liquid stopped, we have the corresponding answer regarding the atmospheric pressure, which acts as well here. Yes. Who was the inventor of this barometer? If you can find in your technical knowledge, general technical knowledge.
Was it Torricelli?
Torricelli, Andra, and Miruna. Yes, Torricelli is the name of the inventor. Thank you very much. All right, and now here you have some instruments, as you can find in use in a bench, measurement bench. So you see different color means different liquids inside. This could be mercury, but it's a little dark. Let's say here on the basis, maybe yes. This could be alcohol or whatever. So you recognize here the manometer, the U-tube manometer, just that we don't know which branch is free. I mean, on which the atmospheric pressure acts, because they are not connected or do not have provided something to connect to a reservoir. But we see that the liquid, the deformation of the column due to the pressure measurement, and we suppose that here we have a higher pressure, either atmospheric, either vacuumetric, depending on the either atmospheric, either manometric pressure. Passing to the right, you identify here a reservoir and the vertical tube. All these are with the on the same type. So explaining the rise of the liquid in the vertical tube when the pressure is applied to the reservoir or to the tube. And then an instrumented U-tube manometer. So now it's clear that this branch is free, yes, and this is connected to a medium. How operates this, as manometer now or vacuumeter? Thinking that the connection was made, yes. Now you can answer us, Ioan, if you can connect.
In the left.
Yes, this blue
I think
is
so.
working as manometer or as vacuumeter.
Manometer, if you have that.
Yes, manometer. Why?
Because have that. I don't know what is his name.
Because the sampling comes here, the sample comes here or acts on the right branch, and as it determines the deformation against the pressure that acts here, this is the atmospheric pressure. So it means that on the right branch we have a higher pressure than here, which obviously is the atmospheric pressure, and it means that it works as manometer. Okay. And finally, we have here a picture of a reservoir with an inclined tube, an original solution to enhance the length of the inclined tube, but not enhance the necessary space for this apparatus. And you see that it starts from 0, the length that we can read, and it stops to 50 millimeter water column. So really micro manometer or micro vacuumeter. All right, so more or less this was what I wanted to present for the YouTube and for the liquid manometers. Let us pass to what we call aneroid or mechanical gauge. They contain an elastic, a mechanical elastic element that will have a deformation according to the pressure that it acts on it. The advantages of using these mechanical aneroid gauges that are really widely spread is the fact that you see we pass from glass instruments to metallic instruments, so the resistance is much more enhanced. Don't speak about construction, which is simple, size reduced, easy to handle, and wide range of variation compared to the previous operation. So they can measure until 1000 bar. This sensing element, which has the deformation, could be a diaphragm, a bellow, or a Bourdon tube. I have some drawings here for each element, but also we can better understand on two small movies. Let us explain first this one. So we have here a membrane, you see, the pressure that we have to measure enters inside, and it will determine the deformation of the membrane, which will be in connection with the pointer of the apparatus, and the pointer will move corresponding to the pressure that is measured. Then we may have, you see here we have an upper membrane and a bottom membrane, so it enhances both sides of the deformation. Or we can enhance more using 4 such elements coupled, and then the answer of the apparatus is enhanced as well. Or below that will expand if the pressure is a manometric one, and again it is in connection with the pointer of the apparatus on the scale. The Bourdon tube, it's a little bit more complicated. It is a question of an elliptic cross-sectional area tube, metallic as well, which will be submitted to 2 deformations. Once this elliptic shape to a circle one, and then the close end will move from position 1 to position 2 if it will measure manometric pressure, or the deformation will be inside this shape if it will work as a mano vacuumeter, so measuring a vacuum pressure. This end, you see, of the tube is in connection with a mechanical mechanism and acts on the pointer of the apparatus. Now, let us see if we have the small apparatus. So, first of all, this one. Do you see it? The change?
Yes.
Okay.
Yes.
Okay, let us look to what is here. Bourdon tube or diaphragm? Okay, Wicca was nice, but let us have a look also to different types of gauges, which enlarge a little bit the field. So you see the pressure acting on the tube and the deformation of the closed end in connection with the needle. Very most application, yes, medium to very high pressure. So keep in mind this variation range. So you see the below that was fixed in my drawings, now it acts and it determines the pointer to turn to the certain value of the pressure. Measuring pressure range below what the Bourdon tube gauge can give. So they are complementary actually. So you see this strain gauge based is actually directly a digital gauge, so you don't see what's inside, you see only the indication, and this is all. That's why it's important also to know the principle and to have idea what's happening inside such digital gauges. So this piezoelectric gauge will be discussed a little bit later as an example of electric instruments, but you have here the digital version. I will present the analogous one, and the digital, again, it shows you this information in variation of voltage, which is proportional to the pressure. Okay, this was also just for your information and to show a little bit how this apparatus works. In the laboratory, I could have shown you directly also what's inside such a representation and how they works, but this is it, we are reduced. Nevertheless, we cannot finish this category without presenting the way that these elastic element apparatus are placed during the measurements. You see in the picture, and this is advised to be like this, the fact that an isolating loop is placed between the apparatus and the medium of which the pressure wants to be measured. This isolating loop, it's very important mainly in three cases. The vapor pressure measurement, The vapor, when it enters in the tube from the duct, yes, it enters in the this loop. Due to the temperature which is reduced, a part of the steam can condensate, and in that case, in the apparatus will enter here, yes, PX, mixture of liquid and gas. Generally, this apparatus allows either gas, either liquid, not the mixture of them. So this loop actually will determine the steam to condensate, and inside will enter only liquid. If it's question about abrasive medium that is handled here, also for this we need information about the pressure. In that case, if we don't have a separation between the two parts, we risk to damage the apparatus. So generally in this case, the loop contains an intermediate medium that transfers the pressure information to the apparatus. When it's question of oxygen pressure to be measured, also we have to take care here to take precautions, because the oxygen is very explosive in presence of fat. So it is better also in these cases to use an intermediate medium between the apparatus and the flow. Also, what is to be noticed here is the fact that for such instruments, the connection to the system is made at the border of the system. The apparatus does not enter in the flow. And due to this fact, the pressure that is measured in this way is called static pressure. Do you know other type of pressure from fluid mechanics? Maybe Bernoulli law? From Bernoulli law? What states Bernoulli law? Andrea? Are you strong in fluid mechanics? Strong informations? What states Bernoulli law? It's a sum of three pressure, yes? One, I mention it. It's the static pressure, this one, that it's given by the apparatus here. Then,
Yeah.
if we enter in the flow and we have the speed profile, this will help us to determine what we call what type of pressure if the speed is involved. Fluid dynamics, it's the name of your course, yes?
Yes.
So dynamics means that something flows and has a certain speed, yes? So
Yes.
if that pressure is based on the speed, it's called dynamic pressure. And also there is another term which depends on the position of the tube compared to a reference. If it's really important, it's the geometric pressure. So Bernoulli equation put these three pressure with plus sign in between and states that the sum is constant. What means this? That if that one can passes to the other one, but the sum will be constant. And there are cases when we use this Bernoulli principle mainly to the air intake in an internal combustion engine where we have a nozzle, and this nozzle determines the increase of speed. So the dynamic pressure is increased, but because the sum is constant, the static pressure is reduced, and this determines the drop of fuel to enter in the air flow. I'm sure that you will study you will have these informations detailed in the course of thermal engines. All right, so these were a little bit the elements that I wanted to point out. So the fact that it is question of static pressure that we get, and the fact that measuring the pressure with these instruments involve special measures, like this loop and intermediate fluid in between the apparatus and flow. The last apparatus that we are presenting is this electronic pressure sensor, or it is having as method the variation of an electrical property. So we pass in the electrical field, transforming the pressure variation in electrical property variation. There are several properties that are involved: electrical charge, capacity, inductance. So I have chosen only one, namely the voltage variation. But before presenting this piezoelectric pressure sensor, let us mention the main advantage of this category, these classes, the fact that it's the only classes that can measure instantaneous pressure, which means that pressure that varies in time, they can emphasize the variation in any moment. And also very high pressures. Very high was also for the gauges, for the book, but here goes a little bit to higher values. All right, so the piezoelectric sensor, you have seen it in the digital presentation. Now let us mention what's the effect that the method uses. It's the piezoelectric effect that is presented by a series of crystals. Quartz, the quartz is widely spread, but there are also what is called cyanide salt and tourmaline. And this piezoelectric effect, you see, consists in generating electrical charges. Maybe it is a good idea to look here in these two blades of crystal that will polarize in, and they are placed in such way that the sign should be the same for the inner contact place. This will, here will be collect the minus sign, and the external connecting blades will be charged by plus, and we will collect it here, giving us, instead of delta P, this is compression, yes, but it's the same also for expansion or stretching. We will have as answer this variation of the voltage. The main disadvantage is that this answer of the apparatus is very reduced and needs strong, but this can be done. So this is behind also these digital instruments, that is actually only a black box with a screen where you see the values, nothing else. The operation range, there are also sensors allowing for very small times interval to measure pressure until 8,000 bar. All right, so this is what I wanted to present very briefly. We do not enter too much in details, but what you need for further applications is here. So if you have questions, first of all, on what was done, do you?
No, until now.
No.
Not quite.
No.
Okay. So in this case, I propose to you to solve together an exercise. I cannot say an application because it's very reduced. It's just for apply the, how to say, the knowledge related to pressure units. Do you have the reference number, each of you?
Yes.
Yes.
Okay, so I don't have to put also the
Yes.
table, I hope, because otherwise I cannot have both in front of mine. So I will put this application on Moodle. I just conceived it after I put all files, just as an application. So I didn't use notation because it's your task to do it. At the exam you won't have the notations of the properties. So according to the text you have to find what notation is used. In this case you have a pressure gauge placed on the boiler that indicates this pressure, 8 plus 0.1 technical atmosphere. We used last time the technical atmosphere. Now you have the explanation why it has 9.81 10 to 4. So you will pass in Pascal this value. Then you have a barometer there indicating you a pressure, atmospheric pressure of 742 plus 0.1 times N millimeter mercury column. And the question is determine the absolute pressure and express it in the main units, which are part of the table: Pascal bar, technical atmosphere, kilogram force per square meter, millimeter mercury, and water column. Okay, so what is supposed to write in front of when we want to compute this is a pressure gauge on a boiler, and it has an important value of that is indicated. It's manometric or vacuumetric pressure. What does the boiler do? Its use is for either producing hot water, either vapor, depends on the application, but the idea is that generally it involves temperature rise. If the temperature rise, the pressure do what?
It will rise.
Yes, so equally rise. So it's a high value of pressure in order to be considered vacuumetric. Yes, so obvious it's a manometric, manometric pressure. Okay, so you will put this manometric pressure notation, yes, and looking to the passage from 1 atmosphere to Pascal, you will add to your value, yes, the passage in Pascal. Who has the lowest N, maybe, and could help us? Maybe Dragos, it's Bukur. He has the lowest one. Dragos, can you
Yes.
do some calculation, and maybe Diana could help you as well to give us your value and to have a reference or the order of magnitude for the manometric pressure.
Wait a second.
So your reference is, I don't have
Mine is 7.
Dragos, you have 7? Okay.
Yes, I have 7 as a reference.
Okay,
number.
but I think that it's the lowest looking to the names. Yes. Okay, 7. I put here n equal to 7. So your value will be
So the pressure gauge is 8.81 8.7.
Okay, 8.7. I will put it in yellow in order to show for each student that it should be different for each of you, but the passage in Pascal, it's the same. And Dragos have got, generally when you give the value here, will be 8 point something, 10 to 5. Yes, you separate 10 to 5 because it gives us a very good reference to the atmospheric pressure. Yes, so it 8 point what? Andra, or who is next to you, Miruna? If you can give also your value, it would be better.
Something.
Miruna, now Andra?
Could I ask you something?
Yes, of course.
From technical atmosphere to Pascal, we don't have to derive?
I do not hear you very well. Please repeat the question.
From technical atmosphere
Yes,
to
to
Pascal,
Pascal. Yes.
we don't have to derive? I don't understand why we multiply.
What's the derivation? One technical atmosphere, it's equal to 1 kilogram force per square centimeter. This is its
Okay.
so kilogram force. It's in the technical system of unit, and it's the equivalent of force in international system of unit. Yes, and the equivalence is done by 9.91. 1 kilogram force, it's 9.81. I do not, a Newton. Okay, so this 9.81, it's here, yes, and 10 to 4 corresponds to the passage from square centimeter to square meter. When you pass here is 10 to minus 4, and at the end it will become 10 to 4. So this is the difference. You can also see this difference looking to the table to what means kilogram force per square meter. You see here you have precisely 9.81. When you pass from square meter to square centimeter here, yes, it is 9.81, 10 to 4. Did I answer the question?
I ask, we have to transform from technical atmosphere
Yes, to Pascal,
right?
Yes. So
And
give me your value.
I have first time, I'm 16 and I have 9.6.
Excellent, 9.6.
Technical atmosphere.
Yes,
And if you want to go to Pascal, we don't have
yes,
to derive is not Pascal, there not has to be 80. Where is Pascal there?
it's Pascal here.
We don't, but in the problem is not technical atmosphere.
Yes, but one technical atmosphere, it's 1 kilogram force per square centimeter. So it's 9.81, 10 to 4 Pascal. What is also in the table. Yes?
Yes, yes.
Okay. So
okay.
Now if you can do this calculation, we will have another reference for n equal to so Dragos, have you can
Yes,
you give me
8.53.
5 to
3.
3. 10 to 5, yes?
Yes.
Okay. So now Andra will give us for n equal to 16, she said. This, not 16, what is your?
22.
22, excuse me, yes, you are 22. Okay, excellent, you are the extreme limit, not
So
the last. So it's 9 point.
It's actually, I got it as 10. It was 10.00.
10? Wow, 10 point something?
0.00, so I left 10.
Okay, so
Times
it's just
10 to
10, excellent, 10 to 5.
power 5, sorry.
Pascal. All right, so this should be N22, okay? All right, so once you have the pressure, the manometric pressure in Pascal, you may pass to express the atmospheric pressure. So the atmospheric pressure, its notation, I prefer B because it's from barometer and it's short and different from this all P of X with something, some subscripts. And you have in the table, let's go back to the table, the passage in Pascal, yes. So actually you see that, and we mentioned when we discussed about the table, that this 1 millimeter is present here, 1 millimeter. So you will replace your value with here instead of 1. Dividing by 750, you get bar, and from bar to Pascal, 10 to 5. Okay, so each of you will, or some, let's take somebody from the middle, who would be Mircea, maybe, or Oana, to give us the atmospheric pressure. Well, we don't have any.
I can give if.
Okay, just to have the limits, yes?
Yes.
Okay, tell us what you have.
I have 0.9.
No, give me first the value that you have replaced, 700 and
44.2.
44.2.
Yes.
Okay, so I multiplied before with 10 to 5 in order to not do mistakes at the end, and you have got
0.99, and I wrote it as 1 times 10 to 5.
0.99.
Yes.
There is something else? Maybe 3 after 0, it's better.
I didn't write.
Okay, the idea is that if it's 9 compared to 2, multiplied by 10 to 5, it's important. Okay, so generally at least 3 numbers after the period should be taken. Okay. All right, and now we have Pascal here. All right, so everyone should be below this value with the atmospheric pressure. And finally, we are in the position now to compute the absolute pressure. You see that I didn't associate the pressure to a state. So you just do the sum of them and give the value in Pascal. So for Andra is what? 10.99 is obvious. 10 to 5 Pascal. Okay. Now what you have to do is to pass this value using the table or as you want, doesn't matter, or directly using this column of passage, either passing, if you want, for example, you may pass the technical atmosphere, yes, into millimeter mercury column, and yes, technical atmosphere in millimeter mercury column. Where is it? Here, 735. And then to do the sum with the atmospheric pressure that you have. Yes, it is also a way. Or you take this sum and you pass in all the other units. Okay, if you have questions, I think it's a very simple calculation. So if you have problems and you still have questions, we can discuss tomorrow from 12 to 13. If not, because we didn't have the break, the time is over. I thank you very much for your attention and your participation. And have a nice afternoon and an easy week that follows. Thank you very
Thank you.
much. I will
Thank you.
stop the records, and this is it.
Okay.
Goodbye.
Have a good
Bye.
day.
Bye-bye.
Bye.
Bye bye.
Bye.